Hello everyone, and welcome to today's chem lesson. Today we are going to wrap up our discussion on the periodic table and the trends that we can see in it by taking a closer look at the periodic table itself. We looked at those four corner elements: lithium, fluorine, francium, and ununceptium, and we used them to help us determine what the trends were, but we didn't actually look at anything other than those four atoms. And so today, in our little summary, little wrap up, we're going to talk about the periodic table itself, right? We're going to look at how this information, which is what we've seen before, right? I took this slide from an earlier video. We knew all of this going in, but now we have a little bit more understanding of why. We know now that the columns have similar chemical properties, and the reason for this is because of their number of valence electrons. Because all of these things have one valence electron, they're going to behave similarly. They all want the same thing. They all want to lose electrons. We know that the rows don't have similar chemical properties because they have different numbers of valence electrons. We've seen this in practice, right? As we looked at our Lewis dot diagrams, as we looked at just any electron configuration. We know that elements in the same row can have similar properties, right? We can have things with low numbers of valence electrons that want to lose, things with high numbers of valence electrons that want to gain, but it's not a guarantee that because things are in the same row, they have similar chemical properties. But beyond that, beyond looking at rows and columns, we also want to look at the types of elements that exist. As we move forward and get more into bonding and talk more chemistry, we're going to look at metals, nonmetals, and metalloids and start to look at how they interact. Now, metals are good conductors of heat and electricity. They're found on the left side of the periodic table. Nonmetals are the opposite. They're bad conductors of heat and electricity. They're found on the right side of the periodic table. And metalloids kind of act as that border, kind of differentiate between our metals and nonmetals, acting as a barrier to separate them. They are partially metal and partially nonmetal. Depending on which metalloid you're looking at, they have characteristics of metals, characteristics of nonmetals, and kind of fall on that spectrum in between. But the big question now is, where is the dividing line? What separates the left side of the table from the right side of the table? What do they mean when they say the staircase? Right, when I look at metalloids and I say metalloids are on the staircase, they separate the left from the right. When I look at the periodic table, what does that mean? Where's a staircase on the periodic table? How am I going to separate my left from my right? Am I going to look right down the middle? Or I should say, right down the middle. Is that going to separate my left from my right? Am I going to use these divots to separate my left from my right? Am I going to do it here? Where's the staircase? What separates the left side of the table from the right side of the table? Good. Right here, we've got a bolded line. right? right, we've got this bold line that runs its way diagonally down the periodic table, looking a lot like a set of stairs. So this line is our staircase. Nice and bold and easy to see. This separates our left from our right. The things that touch the staircase are our metalloids. These elements that share a side with this bold line are going to be our metalloids. And that means that everything to the left is a metal. Everything to the left of these stairs is going to be a metal. Which includes these down here. And everything to the right is going to be a non-metal. Now this points out a number of things. Right? There are way more metals than there are non-metals. And that's fine. That's totally fine. There's nothing wrong with having a disproportionate balance here. We don't need there to be equal numbers of metals and non-metals. This is just the way the periodic table works. This is just the way the elements arrange themselves. We end up with many more metals than non-metals. My highlighting also leaves two important questions. Right? The first being hydrogen, which is a non-metal. Right? Hydrogen is a non-metal, distinctly apart from the rest, right? Hanging out with the metals on the left-hand side of the table. It is the only exception to our left and our right side rules. As for ununceptium, it falls in a weird spot. And really, it's not going to get asked about. But with 7 valence electrons, it's most definitely either a metalloid or a non-metal. But because these elements down here are so radioactive, they really don't exist for long enough to get classified as one or the other. And so it's left out here because it's never going to be asked about, and it's also something that is undetermined as of now. Really, that's true of a lot of these 3-letter symbols, where it's our best guess, but not determined. And these, qualifiers, right, saying that all of these blue are metals, all of these green are non-metals, actually can help us generalize about those properties that we looked at before. We can say that metals have relatively low ionization energy. Right? The trend for ionization energy went to the left and down. To the right and up. So the things that have low ionization energy are down here. Notice that they're all metals. The things with high ionization energies are up here. Notice they're all nonmetals. Same thing goes for electronegativity with a trend that faces this way. The low side of electronegativity is down in the bottom left. The high side of electronegativity is up here in the upper right. And so it allows us to say metals have low electronegativity. Metals have low ionization energy. Metals have large radii. Nonmetals have small radii. We can kind of start to make those broad brush assumptions because of what we learned about the trends and because of what we see here in our little color scheme. But there are a couple of more things we can say about metals versus nonmetals, particularly about their properties. Metals are hard and lustrous, which means shiny. They have high melting points and boiling points, like we said before. They're good conductors, like we said before. They're malleable, which means they can have their shape changed. They are ductile, which means they can be turned into wire. And on the other hand, nonmetals, which have pretty much the opposite set of properties. Brittle, dull, low melting point, low boiling point, bad conductors. So in addition to the trends and being able to say that nonmetals have high ionization energy, high electronegativity, small radii, we can also describe nonmetals with these qualities, with these properties. And this means that we can talk about elements based on these properties too. If we discover something and we need to figure out what it is and we test its melting point and boiling point and find that they have low melting points, low boiling points, we can pinpoint that as one of the nonmetals. We don't know which one, but it helps us tell the difference and narrow down our choices. And that carries forward. If I ask a question like this, which element in group 15 would likely have luster and good conductivity? When we look at a question like this, we're looking for which one of these is a metal. Right? They're describing the properties of metals here, and so we have to check the periodic table, look at group 15, the 15th column, which has N, P, AS, and BI. look at where that staircase goes, and we're able to identify we've got nonmetals, metalloids, and a metal over here, which pinpoints our answer down to choice 4. And that's really all that there is to say about that. And so I'm going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.